Today we're going to discuss Le Chatelier's principle. When a reaction is at equilibrium, if there is a stress of some sort placed on it, the equilibrium will shift to relieve that stress. Let's analyze a few of these words in that statement. First of all, what does shift mean? Well, a shift means that it will produce more of either the reactants or the products to reestablish that equilibrium. So if I shift to the reactants, it means I'm producing more reactants, or if I shift to the left. If I shift to the right, I'm going to produce more products. The word stress that I use can be in the form of a change in concentration, a change in temperature, or a change in pressure if you're just dealing with gases. In general, you'll find that the system will try to counteract whatever change is applied. It will not change the equilibrium constant as long as the stress is not the temperature. Remember, temperature will always change the equilibrium constant. But it will change how many reactants or products there are. Let's look at the example of the reversible reaction between hydrogen and nitrogen gas to produce ammonia. Take a moment to write this equation if you can. All right, so we have a balanced equation here, the production of ammonia, and you'll also see that I have that the heat of the reaction is negative. So that helps us to remember as well that this is an exothermic reaction, meaning that heat can be treated in this case as a product because it is released. If I would calculate the equilibrium constant given the concentrations, I don't have the numbers here, but if we, at room temperature, the equilibrium constant is approximately 0.01. So what does that mean? Which is favored, the reactants or products? Well, the equilibrium constant is less than 1, which means it will favor the reactants. This equation is famous as known as the Haber reaction. And either you've read about Fritz Haber or you may read it in your class, but it's an interesting story. Around 1900, there was an ammonia shortage, and ammonia was used as a fertilizer, and it was important for food production. It also could be used in explosives, which is another side of it. But many chemists were trying to use this reaction to produce ammonia in order to get more. Le Chatelier abandoned his research after an employee of his nearly died in an accident, but Fritz Haber and Karl Bosch successfully developed this process using this Le Chatelier's principle of creating stresses to shift the reaction. In this case, he would want to shift it to the products. He also used catalysts and high temperature and pressure. This ended up in him being rewarded with the Nobel Prize, but also was investigated for war crimes because of the chemical weapons that were developed as a result of his research. When using this reaction, about 99% remain as reactants and only 1% actually remained as products. Remember, the goal is to produce more ammonia. This isn't a very good percentage when you want to get the ammonia. So how did he use Le Chatelier's principle? Well, first let's look at the stress of concentration. When a stress of concentration is applied, a reaction will shift away from an increase in concentration and shift toward a decrease in concentration. So as we look at this particular reaction, we want to produce more ammonia. We want to shift toward the product. So what would I have to do with the hydrogen? Well, I want it to shift away from the hydrogen towards the ammonia. So if I want to increase the products, I'm going to have to increase the hydrogen concentration. If I look at the nitrogen, the concentration of the nitrogen, again, I want to shift it away from it towards the products. So I'm going to have to increase the amount of nitrogen. So if I increase the hydrogen and the nitrogen, I'll shift it and create more ammonia. Now, on the other hand, what happens if I change the product? How would I change the amount of ammonia in order to produce more? Well, I want to shift toward the ammonia, so I would decrease. As the ammonia was formed, it was removed, causing the reaction to produce more, to shift in that direction. Another factor that can be considered is temperature. As I mentioned before, we first need to determine if the temperature or if the heat is treated as a reactant or a product. In general, we can say if it's exothermic, then heat is treated as a product because heat is given off, it's released. If it's endothermic process, then heat is treated as a reactant because it needs to be added so that it can be absorbed. And then you can treat it just like the concentration. So again, if you want it to shift toward the products, in this case of the Haber reaction, we said that it was exothermic. So exothermic means that heat is a product. I want it to shift toward the products, so if I decrease, it will try to produce more of that ammonia. The third stress we're looking at is pressure. This focuses on gases. An increase in pressure causes the equilibrium to shift toward the side with fewer moles of gas, whereas a decrease in pressure causes the equilibrium to shift toward the side with more moles of gas. Why is this? Well, changing a gas pressure is like changing the concentration. If I increase the pressure, then there are more particles in a smaller area. Increasing the pressure is like increasing the concentration. So, if I have more pressure, that's a higher concentration, it wants to get rid of that extra stress. So it's going to shift to where it would be fewer particles, fewer molecules in the same amount of area. So it'll shift toward the fewer moles or the less moles of gas. On the other hand, if I decrease the pressure, now it's like there are fewer molecules in the same amount of area, like it decreased the concentration. So if there's less pressure, it wants to replace those molecules. So it's going to shift towards more moles. Again, in this Haber process, if we study this in terms of pressure, we'll notice that on the reactant side, we have 3 moles of hydrogen and 1 mole of nitrogen. That makes 4 moles of gas. Versus on the product side, I only have 2 moles of gas. So if I want to shift it toward the products, again, that's our goal here, to produce more ammonia, I want to make it shift to the side with fewer moles. Well, in order to shift to the side with fewer moles, I need to increase the pressure. Volume can also be affected when it comes to gases, basically because it's a change in pressure. Boyle's law is a law that states that pressure and volume are inversely related. So if the volume decreases, the pressure increases. If the volume increases, the pressure decreases. So if you look at this in terms of the Haber process, again, it's going to be kind of the opposite of what we had with the pressure. I'm going to need to decrease the volume because that would essentially increase the pressure, making it shift towards the side with fewer moles. So after applying all these different stresses to this reaction, we could look at, first of all, concentration, where you increase the nitrogen and the hydrogen concentrations and remove the ammonia as it's being produced. We could also decrease the temperature to make it produce more ammonia and also increase the pressure. They found that the equilibrium balance actually became closer to 50% reactants and 50% products. Quite a difference from 99% reactants and 1% products. But since ammonia is collected and the reactants are recycled, you eventually get a 97% yield. This ended up saving lots and lots of lives by being able to produce the food needs for many, many people. In fact, this reaction is still, or process is still used today. All right, let's look at another example of Le Chatelier's principle and see how it applies to a different reaction. In this particular reaction, we want to shift it to the right to make more products. You'll notice it is a positive heat of reaction, which means it's endothermic. So heat is treated as a reactant. So now let's take a look first of all at concentrations. So phosphorus pentachloride is a reactant. We want to shift away from the reactant to the products. So to shift away, we're going to increase the concentration. For phosphorus trichloride and chlorine gas, those are both products. I want to shift toward it. So if I remove some of that and decrease the concentration for both of those, I will get a shift to the right to make more products. Temperature. We said that heat can be treated then like a concentration. And since it's a reactant, I want to shift away from it to produce more products. So if I increase the temperature, I will produce more products. Next, let's look at the pressure. On my reactant side, I have 1 mole of gas. On my product side, I have 2 moles. So I want to shift it toward the side with 2 moles, which means that's a greater amount. I want to, in order to make it shift toward more moles, I have to decrease the pressure. And volume would be the opposite. Remember, we said they're inversely related. So if I increase the volume, it would be like decreasing the pressure. Let's look at some true or false. I don't think the page number is correct here, but we could still look at the true and false. Take a moment to see if you can answer these questions and then check your answers. All right, let's take a look. A reaction shifts toward an increase in concentration. That should be false. It actually shifts away from an increase. It shifts toward a decrease in concentration. Number 2, adding heat to an exothermic reaction makes the equilibrium shift toward the reactant side. Well, if it's exothermic, heat is like a product, so I want it to shift toward the reactant side. Adding heat, yes, will indeed make it shift toward the reactant side. Heat is a product, it'll shift away. An increase in pressure causes a shift toward the reactant side. Well, the problem is we don't really know anything about the moles. So we're going to say false because it actually shifts toward whichever side has fewer moles. That may be the reactant side, but it could be the product side. Number 4, changing the volume of a reaction will not change the equilibrium concentrations. That is false because we said changing the volume will change the pressure of any gas in the reaction. All right, a couple more examples, and these are similar to what you will see on your homework. Let's look at the reaction number 3 here. What would happen if I add HBr? Well, HBr is a reactant. We know that if you increase the concentration, then it's going to shift away. So I'm going to draw an arrow. It's going to shift toward the products, away from the reactant. By the way, make sure you're trying these. Pause them if you need to. Pause the video and see if you can get it right and then check your answers. Let's look at the second option there. B, heat is added. Well, first you have to recognize that the heat of reaction is positive. That means it's endothermic, which means heat is treated as a reactant. So Now it's the same as A. If I add heat, it's going to shift it away toward the products. Shift it to the right, as we would say. In the third situation there, volume is increased. Well, volume will have an effect on pressure. So let's take a look at the moles of gas. On my reactant side, I have 2 HBr, that's 2 moles of gas. And on my product side, I have H2 and R2. That's also 2 moles of gas. So in this case, volume is not going to have any change because there's equal amount of moles. Let's look at the next reaction. Again, in A, H2 is added. We're changing concentration, but this time it's a product. So remember, it'll always shift away from an increase. So in this case, it's going to shift it to the left or shift it to the reactants side. What if pressure is decreased? Again, pressure, we're looking at the moles. Now remember, it's only the moles of gas. On my reactant side, iron's a solid, so we can just ignore that. I've got 4 moles of water vapor. On the product side, the iron oxide is a solid. We're going to ignore that, and you'll notice I also have 4 moles of hydrogen gas. So again, there's no change because there's an equal number of moles. Now what if I increase the temperature? Take a look. My delta H is negative, means it's exothermic. So heat would be treated as a product. So we're very similar to situation A there, where if I increase the temperature, it's going to shift away from the heat towards the reactants, towards the left. Hopefully you feel comfortable and are ready to do examples. As always, if you have questions, make sure you write them down and ask. Have a great day.